So welcome again to C++ course, Advanced C++ for HPC. We had a similar course last year that was designed in a very general way. This year we wanted to be more oriented to HPC in some sense. I'm pretty sure some of you will be disappointed because HPC is not so clearly defined field. So what we intended by HPC will be clear during the course. This course has been prepared by me, Mauro Bianco, works here at CSCS, and in the Future System group, and also by two other people. One is Paolo Crosetto from ETH, and Christopher Bignamini on the back there. And you will see these guys in the next couple of days presenting quite interesting stuff. The idea behind how we designed the course was to think about what is that we wish someone would have taught us in a C++ course. It's like, okay, if I really someone explained me this, I would save myself so much pain because I would have understood what was going on. So that is the main idea. Now, let's see if we implement it well. And this is the first time we do it in this format, so be patient, and if you have questions and doubts and everything, please feel free to raise your hand and ask any question you have in mind. We assume certain knowledge of C++, a pre-knowledge of C++. It might be too little, might be too much. If it's something you don't know, raise your hand, ask a question, and we'll help you. We'll try to explain as best as we can. But now let's go to why you're here. And I guess you're here to know something about C++. But let's say you want to know really why you're here. And so we'll pass the mic around the room. And if you kindly present yourself, tell why you're interested in C++, and that would be very interesting for us to know.
Hello, I'm Gerardo. I know a bit of C++. Okay. Better. So my name is Gerardo. I'm here to learn what of the new features that that were added to C++ in the recent update, C++ 11, C++ 14, and their impact on performance.
Hi everybody, I'm Gabriel. I'm working together with Gerardo, and I never had a proper training in C++, so I want to know how the real pros are doing it, and also learn about the new stuff, as Gerardo already said.
I'm Alberto, and I'd like to learn C++ in order to use it with its new structure to parallel computing increase powering.
I'm Andrea. I'm programming in Genoa, and I like C++ to know new feature in HPC.
Hi, I'm Dario. I'm a C++ developer for a company in Genoa, Italy. I develop a PPBX written in C++. In particular, I'm responsible for signaling libraries like ACDN and SIP. I'm interested to learn more about new standards C++ 11 and 14.
I have a request from the back of the room. If I understood correctly, if you can stand up and look at the camera so you can Yeah, the guys in the front were lucky. No.
Hi, I'm Gigi. I'm working at CSCS. I'm a Fortran developer, and I would like to learn how to write good code.
I am Maxime. I'm part of Future System. I'm sharing office with Mauro and Paolo. And I would like to know exactly what are they doing every day. So,
Hi everybody, I'm Kian. The last few years I've been writing C++ for tiny microprocessors in embedded systems, and now I happen to work in the HPC field, so I hope that I will learn what modern C++ offers for HPC.
Hello, I'm Alberto. I work here at CSCS in the Systems Integration Group. In the past, I've worked with C++, but now I'm interested in getting fast introductions from the expert on the more advanced features.
Hi, I'm Will. I'm also from CSCS. I'm also a Fortran developer, and I'm here trying to prove that an old dog can still learn new tricks.
Hi, I'm Victor. I want to update myself with C++ in HPC.
I'm Sebastian. I use C++ every day, and I'm already familiar with what was being considered a state-of-the-art 10 years ago, and I'm here to learn what's been going on.
Hi, I'm Timothée Dulbach. I'm a cosmologist at the EPFL, and I'm interested in C++ to do efficient data analysis for time-consuming tasks.
Hello, I'm Mohammed. I'm a computational chemist, and I hope that this course is not too advanced for me, but let's see.
Hello, I'm Lucas. I'm working as a postdoc on UZI. We are developing a C++ library for solving some non-stationary modeling problems. And I want to know what we are doing wrong, so let's see. Thank you.
Hello everybody, I'm Ahmed. I'm a PhD student at University of Basel. I'm doing my PhD in computer science. I'm already familiar with writing high performance computing for using C, but I want to know what I can gain if I switch it to C++, especially if I can write high performance code in object-oriented style or not.
Hi, I'm Ali. I'm from the University of Basel, same group as Ahmed. I'm here to learn how to write efficient C++ code for high performance computing.
Hi, my name is Dominic. I work as a PhD student at PSI, trying to solve some statistical mechanics problem and hope to learn how to speed up my code efficiently.
Good morning, everyone. I'm Svetlana from the University of Zurich, and I work in the field of scientific computing, computational fluid dynamics, and well, our group are already users of CSCS facilities, and we have part of the codes written in C++, but I want to learn about some new practices, new things, and how to do HPC more efficiently.
Hello, I'm Jean. I work here at CSCS in scientific visualization. I actually work with two very large software projects which are over 5 million lines of code, each of them. I don't write very much C++, but I read a lot of code that somebody else is writing, and these people are smarter than me. They write codes that I don't understand, so this is my purpose.
Hi everyone, I'm Federica. I'm a PhD student at the ETH Zurich, trying to study our galaxies in our universe. And I had a self-training C++ during my master. While my PhD I'm using a lot of Python, so I think it's a good chance to learn more about C++.
Hello, I'm Andra and I'm from Ostrava, and I developed some library for HPC, and I want to learn something about performance of new features in C++.
Hi, I'm Standa. I'm also as my colleague from Ostrava from Supercomputing Center IT4I, and I'm C++ developer part-time, so I'm here for update my knowledge.
Hi, I'm Matthias. I'm from Frankfurt. I'm a derivatives quant, and I'm curious to see if I'm leaving some performance on the way.
Hi, I'm Vincenzo. I'm a computational chemist, and we work quite a lot with CS and with HPC. I'd like to learn a little bit more about C++.
Hi, I'm Jörg. I'm from the University of Lausanne, and I'm a geophysicist, and I'm currently developing a code to model a fractured geothermal reservoir together with Uzi, here also in Lugano. And we use a framework that is based on C++, and yeah, I code already a bit in that, but I definitely need to know a bit more about C++ to do that really good.
I'm Tim. I'm also working here at CSCS, and I guess I'm one of these traditional Fortran and C HPC programmers. And so over the last few years, the HPC ecosystem has been a lot more enriched by new programming languages, and so C++ is obviously becoming more and more important.
All right, thank you. We have a quite diverse audience. Let's see how it goes. Yep. So when they asked me to prepare a course in C++ for HPC, I started wondering what is practicals. Practical things. So all our code, the code that we're showing here, it would be in a Git repository in a GitHub. It's called example CPP. It is under the Paolo account. The slide will be placed into a link on the web page of the event. There will be a zip file with the slides on there. And if you don't have on your laptop a C++ compiler for some reason, or you have problems connecting somewhere, you don't have a Git or something, we have accounts for you on our system. So if we need an account on our system to run the examples or to do some exercises, please ask here. I give you a username and a password that you can go in. To compile the tests, you have to check it out. Check out the repository from the GitHub, and you create a folder called bin inside there. Okay, it's not mandatory, but it's a good idea to create a build folder in there. Enter into that folder and run cmake ../code, and that will create the make files or whatever project files you need to make. And then you have if you are on Linux or Mac, you can just run make help to see what are the targets that are available, or you can run make to compile all the examples. They should all compile very nicely. We had a fix this morning for GCC 6.1. So. Okay, back to business. If you have any question, anytime, please raise your hand. So as I was saying, when you asked me to do the course in HPC, I said, what is HPC? I'm not really sure I know the answer, but the idea is that high-performance computing has something to do with performance. The problem is that to measure performance is difficult. Actually, you have to define what performance is for you. So what is it? Is efficiency of resource utilization? Is algorithmic complexity? Is energy to solution? What is it? It depends on what you're doing, okay? Every one of you will have a different metric to measure performance. And the idea is that whatever method you choose, C++ may help you. In HPC, I would say there are two major modes. I call it the HPC modes. One is the research codes approach, or codes that are developed in a short time and they have to produce certain values, but they're not necessarily the output of the code itself. For instance, you want to prototype something, or if you are a computer scientist, you want to write an algorithm, a parallel algorithm, you want to measure how well this algorithm performs on a given architecture. And usually these codes require very short runs to collect architectural information, like how many cache misses or how many instructions per cycle you are running, and these are the results. Another kind of research code is a scientific code. You want scientific results. So you are simulating a molecule, you are simulating a star of a galaxy, something, and you want the result of. You want what's happening physically. So you're not really interested in the architecture. It happens that if you want those results, you need to understand the architecture, and you need to exploit it, but it's not that you really care about the architecture, you just want the scientific results. And these usually require quite long runs, so you need an allocation on a supercomputer and have to run maybe a few days, a week, or whatever. But they say that the lifetime of the research codes are really related to when you have the results back, or when you have to write the paper, or when you have to publish something, etc. So it's not really that you care about your code so much. They say this code has to be really, really, really well written. The other mode is when you run HPC application in production applications. So you have a code that requires long runs, and also is lifetime. The lifetime of the code spans multiple hardware generations. And there the problem becomes slightly new. Before, we just had to write a very efficient code. We wanted to get it down to the hardware as much as we can. Here we care that the code will survive a long time. It needs to be read by multiple people, need to be developed by multiple people, etc. So in this case, the programming language and the methodology is basically dictated by the time to deliver and the objective that you have. It doesn't matter, right? You write in Fortran, you write in C, you C++, Python, whatever is the thing that allows you to make that assessment or to get that particular result. In the second mode, the mode of operation is slightly different. You choose a programming language, you choose the methodologies. We'll talk later about what they are. And they are dictated basically by maintenance cost. This is the highest cost when you develop a software. It's not the time you write the code. It's the time you have to keep it for 10, 20 years to keep it alive and functioning. One problem is that there is a transition often. Someone starts with the little research code, little prototype that gets so famous and popular that becomes used by many people, and suddenly it becomes a production code. And there, if you don't manage that transition nicely, you might get into issues in the long term. So why this introduction? Well, because if you're here to learn or to know more about C++, what you really want to know is what is C++ and why is C++ helping in this in the HPC scenario. First of all, the C++ has basically two fundamental features. It allows you to do overhead-free abstractions, or with minimal overhead given by your constraints, and it allows you to develop robust and safe code, a code that once it's written will work. And whoever is using that code will never be surprised by how it will work. And we will see in this course, we will basically investigate some of the features, some of the techniques that allow you to write overhead-free abstractions, allow you to write safe and robust code. One thing that we'll be talking all the time is RAI, which is resource acquisition is initialization, but there are many others, and our goal is to show you that you can do it in C++. We will not investigate much about parallel programming in C++. We have a session about C++ threads. There is a course in the next couple of days, Thursday and Friday, on HPX, which is a library that allows you to do multi-threading very nicely. We will not focus much on the parallelism, but on the fact that if you don't have efficient threads, it doesn't matter how well you run in multiple threads. You need an efficient single thread. Performance, first of all. And so the idea is why C++? Well, C++ is, first of all, very well supported by basically all the hardware, because there is a huge industry behind the scenes that simply work to make C++ on every architecture you can possibly think of. It runs on Mars rovers, it runs on nuclear plants, it runs on operating systems, it runs basically everything. It's also very well integrated in IDEs, so Eclipse, NetBeans, or Visual Studio. There are many available compilers which are standard compliant. And there is a huge online community. Basically, you need something, if you know how to formulate your question, you find the answer very, very quickly. And one is a Stack Overflow. I hope everybody knows what Stack Overflow is, because it's the first thing you hit when you ask something on Google. And another one is cppreference.com, which is a site that includes very nicely all the standard features of C++. And most of all, C++ allows you to write abstractions, so it allows you to compose, to write components and connect them without overheads, so very efficiently. And so your application complexity can scale up. You can develop very complex applications because you have all these components that work nicely together and efficiently. It's very easy to make components work in a very nice way. Consider Python. It's very nice. You write Python thing and it works, right? Whatever you write a module, you write a function, you pass something to that function, and that works. But it is slow, and it is intrinsically slow. So there are three main concepts that C++ allow you to deal with, which is separation of concerns, fast prototyping, and incremental optimizations or extensibility. It basically allow you to step out and design interfaces, separate concerns between user-level code and library code, It allows you to separate between data structures and algorithms. Usually, if you write C++ code as a prototype, and if you write it nicely, it will be kind of ready to go into production mode quite easily if you follow certain guidelines. And incremental optimization and extensibility is basically the idea that you can always specialize your code, you can always improve your code without having to disrupt anybody else's work. All of this boils down to the fact that you need to think about other people working on your code, or even yourself in a couple weeks maybe. But the idea is to think about the code as an artifact that, if it's well done, it will survive a long time. This is why, strongly put as this, when you consider C++, when you consider what programming language you want to use in your application, and you have many choices, well, why you want to use C++ in certain conditions. C++ is a very complicated language, okay? You can shoot to your feet in so many ways. It can be so disappointing many times because you just find weird stuff going on. But it also gives you the ability to do very good work. So first of all, there should not be C++ without API design. API design, application program interface. When you write something in C++, the first thing you should think of is, what is the interface of this thing? And then you think about the algorithm, about the implementation. Should I use a pointer? Should I use a counter? Should I use something? After, that comes after. There should be unit testing. Who is doing unit testing on the code? Oh, okay. Better than last year. Last year was only one guy. So we're getting better. We will go into all these points shortly, because I really want to stress this is the environment in which I want to present this course to you. You need the test-driven development. Who heard about this technique? A few. Okay. Okay, there are books written in this. I didn't read any of them, but I went to Stack Overflow a lot. You need systematic application of methodologies. And we will talk about this. And you have to limit the violation. If you're working on a team of people, enforce these rules. You say, no, this has to be done this way and not the other way. You have these methodologies are very important. You need coding standards. Yeah, we'll tell you why in a bit. But basically, if you have this thing, if you apply these things, then you will find that your code will be very robust, it will survive a long time, it will be kind of easy to maintain. Of course, we don't have to be too extremist. This comic here is how to write good code, and you want to write fast code, or you want to write good code. And if you want to go faster, you go faster, but you will go back into writing fast code. Or if it's not good enough, you go back in writing better code, and basically nothing will be put inside the good code. So you need kind of balance between doing the things right and doing things all together. So first thing, unit testing. What is unit testing? Well, the idea is that every component, every function, every class, every member function of your classes should be tested. For example, you have a function to compute a value. We'll check that the value is being computed. Or you want a data member that should satisfy some invariance with something else. You have to write a test to check it. Or you want to check that the value is always available at compile time. We will talk later about these things, or tomorrow. And you have to write a test that checks that these things are actually true, that this thing happens. There are a few things that cannot be unit tested. Main cannot be unit tested, your main function. And this is why you should always keep the main very, very short. And also the static assert. If you never heard about static assert, don't worry, we will have plenty of examples of static assert later on. And to do this unit testing, there are many testing frameworks you can use. One is Google test framework, the Boost test framework. C++ doesn't offer one. There is a proposal in the standard committee to have some kind of testing infrastructure. Probably it would never see light, but let's see. But this unit testing can be very, very complicated. I mean, it might seem easy, but it's not. This is the function that returns a random number, which returns 4. And the comment says, well, I throw a dice once, that was 4. That's a random number, and you get always 4. So how do you test that the random number is really random? It's very complicated. So the test can be sometimes very convoluted. But nevertheless, it is very important to have it. The test-driven design or development instead is a different approach, is a different philosophy. Basically, before you develop a feature, a function, a class, or anything, you write the code that uses it. Instead of writing the class, you write the code that uses the class. Instead of writing the function, you write the code that uses the function. And this allows you to think as a user, first of all. So you sit in the, you put yourself in the shoes of the user, and this helps in designing better APIs. So who is going to use that function will be really not surprised because it will be designed in a very natural way. APIs are the most durable things you will ever write. Okay? When you write an API, if it is adopted, you're stuck with it. So you better get it good, otherwise people will be stuck with a bad API for the rest of your life. And everyone is an API designer, okay? You might think you're writing the code for yourself, writing your own little research code or something. Then you go back in a couple of weeks and you say, what the hell was I thinking when I wrote this thing, right? So everyone is an API designer. And also beware of the transition from research code to production code, right? If you start with the good APIs, as you write the code, the first thing you think is that what is the API for these things? It helps you getting better code as you go. I also applied the desire-driven design, which means I just sit down and say, how would I like to have this thing running? And I write it and I say, okay, I cannot. C++ doesn't allow me to do this, so I relax here and there until I get the best thing that I possibly can have. Now, it's not perfect. Nothing is perfect, but it helps you in getting better code as you go. And the methodology, you can find it online someplace, this acronym, which is KISS, which is keep it simple, stupid. And the idea is that, yeah, do not show off, right? Write the code write what the code is supposed to do. Don't try to be too smart, but you have to be smart. When I talk about methodologies, what I mean about methodologies, well, for instance, adhere to rules. And rules might be, when you write the class that implements RAI, resource acquisition is initialization. We will go into this very often. For instance, it means that no one using that class should never use the new statement. The new statement is the new goto. Okay? If you use goto, you are evil. Now, if you use new, you are evil, the same level. Not quite, but almost as evil as goto. It's a very nice comic, I think, here. I really enjoyed. But anyway. So every function should be n lines long. So don't write functions that are 5,000 lines of code, because they're basically impossible to read. And it's very difficult to have a function that requires 5,000 lines of code and cannot split into smaller pieces. C++ is a nice feature, which is massive inlining, which means don't be afraid of calling functions. It's not Fortran. Fortran, when you call a subroutine, you call a function, usually you call the function, and you call the subroutine, you put the stack in the stack frame, you put a pointers around, you jump it into a function. C++, if you optimize the code, would never do it. Would just inline everything. Comments, write the comments that explain what is not already written in the code. If the function is short enough and the code is clear enough, you just read the code to know what the code is doing. You don't need a comment saying, oh, this function is adding a plus 1. Another methodology could be review the code upon pull requests. So I hope everyone here is using a version control system. I hope that this version control system is Git. And then in Git, you can say, when you post the code to someone, say, this is my code. Could someone in the team review it? And you get feedback to improve the quality of your code. Very, very important. And then run automatic test suites, for instance, every day. And there are more and more rules. The idea is that C++ is a very complicated language. You can shoot your foot many times in many different ways, as I was mentioning before. You never know when you do something, there might be consequences that you would never forecast. For instance, in this comic, you say, this guy will say, okay, well, I can change all my program, or I can put a go-to statement, what might get wrong there, and then you have a velociraptor jumping from somewhere and eating you. This is actually, well, it's not a real experience, but it's what will happen, right? You never know what the consequences can be. It might be several. But let's go and see some code. So who's able to tell me what's wrong with this code? Yeah, the using statement add the global scope. If you do using namespace something, put it inside the scope. For instance, inside main and not in the global scope. Okay, using in the global scope is very bad practice. What else? Yes, main cannot be tested. Good point. There should be a function that takes a stream, and then you pass a string stream to it. You get the string back, and you check that the output is right. This is a very short example, so let's say we don't do it, but it's a good point. Comments? Yeah, completely useless. Who needs to know that this thing is printing a hello world? Who needs to know that that is a main function? We know it. So don't write comments like this. They waste time, they waste space. What else? And the line, yeah, what's wrong with that? Yeah, actually, yeah, it's not even said that NDL flushes, but you're right. Use /n. It's more efficient. You will get the output anyway. You type less, so put \n in there. Good catch. Other things? Return 0. Did someone, apart from him, know why the return 0 is not a good practice? Okay, want to keep it yourself and share?
Shouldn't the default return value always be 0? So you could just return it?
Okay, you say, is the return value should always be 0? No, it's system dependent what the success return value is. Different operating systems have different conventions. So if you return 0 and you run this code on some operating system that doesn't have this convention, basically the code fails every time. They say, oh, something went wrong here. So instead, you should not put any return statement. The main is a special function, the standard specified. The main is a special function. You don't need to put a return statement unless it's different than 0. And so if you remove that statement, everything will work fine. So we should have covered everything. We should using a global scope, useless comments, superfluous, not portable return is backslash. Also the use of, which is back to what you were saying before, kind of similar things. Basically, cout is a global variable, and you should never use global variables. Of course, you have to use cout to printing, but if you put your function, you pass a stream in, then you can also do unit testing. Other methodologies goes more into, so the first slides on the methodology is like very high level. It's like meta things. So how you write your code, how you write your functions, so how many lines of code you should have. Another thing, when I design a class, when I design an object, how should I design my classes? And the main idea is to try as much as you can to implement concrete types. What is a concrete type? So the general way of getting these ideas, it behaves like an integer. It can be copied, can be assigned, can be moved, and basically anything that behaves like an int. And there are 3 rules. So if you write a class that doesn't need special constructors, is a class that just works out of the box, then you don't need any constructor, and you don't even need a destructor for this class. So the compiler, as you probably know, introduce for you certain functions in your code, which are typically constructors and destructors for your objects. We will go into this more in these days, actually. It's quite interesting. So if your class doesn't require anything, just don't write anything. The compilers will implement the right thing for you. If your class needs a user-defined copy constructor or copy assignment, then it probably needs also a destructor. If it needs a destructor, it probably needs a copy constructor or a copy assignment. Anyone knows what I'm talking about? So we know what a copy, what is the destruction of an object is. If a class needs to be moved, we'll go into move semantics more tomorrow. Then we probably need all of them. If you need to be moved, you probably need to be copied. And if you need to be copied, you need to be destructed. So you need a special destructor. And there are many cases in which the rules do not apply. For instance, when you have move-only objects, like unique pointers, and what are the other ones? Threads? Thread blocks. There are objects that can only be moved, they cannot be copied. So these rules are kind of fuzzy there. But when you design a class, try to adhere to these objects, to these rules. We'll go into this some other time. So RAI, resource acquisition is initialization. This is a new concept in C++ 11, actually. C++ 3 and they tried to have something like this, but they couldn't because there were not enough semantics to express it in a nice way. But the idea is that when you construct the object that requires, so if an object requires certain resources, like a piece of memory, a lock, a bus on the system, whatever resource it is, a printer, whatever, then it requires that resource at construction time. So you don't construct the object and then gather the lock. You gather the lock when you construct it. The same thing for the memory, etc. And the resource is released at destruction time. So when the object dies, it goes out of scope, get destroyed, the resource is released. If the construction happens to not find the resource that is looking for, you should throw an exception, or should kind of die there. It should signal some error. So construction and destruction. If you use a resource like a memory chunk, if you use a lock, my imagination is running low, if you require some other hardware resource of any kind, then you always do it through write class. You never acquire the resource yourself. The user of that class should never run a new method, a new function, just, for instance, allocate something on the heap. This might be a little too technical, but basically, suppose that you are using your I class, you are instantiating your object, which grabs some resource. Some way down in the code, some error happens, and an exception is thrown, so an error happens. Well, that will leave the resources hanging if the object is not destroyed. You allocate the object, you grab the resources, an error happens, everything crashes, your object stays there. With RAI, it doesn't, because of the stack and winding technique. We don't go into that, but basically, when the error happens, the resource is freed, is released. If you do a new statement instead, you allocate a chunk of memory, you go on in your function, there is an error, things barf, everything crashes, the memory is still allocated because your delete or your free is after that error happened. And so the RAI semantics has been made possible after C++11 by the introduction of the move semantics. Is everybody familiar with move semantics? Everybody knows exactly how it works? Hopefully not, because I have a long presentation about it. All right, great, awesome. It's one of the major introductions in C++11 with this move semantics, and it might be very confusing when you look at it from the wrong angle. So it's important to see it to the right lenses. I hope to be able to give this right lens to you. Coding conventions was another bullet that I had there, and it's why do you need coding conventions? First of all, what is a coding convention? It's like, okay, when you write a function, put the curly braces at the end of the line, or put it at the beginning of the next line. When you write when you have a data member of your class, put an M underscore in front of it, for instance, or some other convention, put underscore after the name or something. These are a simple example. For instance, S underscore name is a static data member of my class. If I have a capital letter, that is a template argument name. There are many coding conventions out there. The most used one is basically the Java one with the camel case. This is more like Boost and STL. But why are these things very important? It's important because when somebody else look at the code, or even yourself in a few weeks, look at the code, it doesn't have to spend time looking at what is this symbol, what this thing. You see, you look into a function, you see a name, and you say, what is this? Is it the local variable? Is it the global variable? Is it, what is that? If you have a name conventions, then you can simply not even think about it. You say, okay, this is a data member of my class. Ideally, before starting a project, there should be a discussion your team that says, okay, what are the coding conventions that we should apply here? And try to find consensus on it. And if this thing can be really, really horrible, like people fighting on the curly braces or a semicolon, and it just doesn't make any sense. Just agree on something, and everybody should do exactly that, so people can understand each other's code easily. And if you do code review, when someone writes the code and push it into your repository, somebody can go there and review the code and say, no, you didn't follow the coding convention here, fix it, etc. And the main aim of the coding convention is to make the code readable. You don't want to waste time reading code. You want to write code. C++ offers books, entire books on the design patterns, on how to implement certain functionalities. There are so many of them, this kind of jungle. I mentioned here a couple of things, the CRTP, type erasure, proxy, visitors, but there's no pimple and whatever not. So there are so many patterns there. It doesn't make sense for us, I think, to show you these patterns or to make like a long list of patterns, because it depends on what you need. We are going to discuss the CRTP pattern. It is a curiously recurrent template pattern, and the proxy pattern, because they're things that we find useful. We have found these things very useful in our daily job. But the others are very, if you search online for C++ design patterns or idioms, you will find plenty of information about these things. What are we trying to cover with this course? All these items. Hopefully we'll make it. I'm not sure. I'm still confident that we can do it. There's a lot of stuff. From the basics, like value initialization, which is very tricky, actually. In C++ 11, they added even more way of initializing values of your objects. And you need to know what's happening, basically. Name lookup and type. Deduction, when you write the function, how does it get seen by other components of your code? Move semantics, lambdas, standard functions, memory management, templates and template, meta programming. What is the feeling of the room about template and meta programming? Does someone used it? Okay. Very powerful technique. Need to be used with care, but it can give you extremely good code. Generic programming. Does someone knows what generic programming is? Have you used STL, standard template library? Kind of, right? That is a generic library, technically. And it's a way of writing code to be really general and usable. We will go to the patterns I was mentioning. We'll talk a little bit about the standard template library. Not really much, just the thing we think makes sense. Global variables and static initialization. This is something that is a kind of off topic for all the rest of the course. It's like a self-contained thing, but it's very, very useful because it can be extremely confusing what's happening there. And we go into multi-threading, and also you have some random number generations light. That I suppose that being some scientist in here, you need random numbers at some point in your life. So, and to finish, to conclude this introduction, hope it's not too long. This is how we designed this course. We didn't want to just give you a list of rules or a list of language features that you can use. We want to explain you why things happen in a certain way and not in another way. I think this is what makes this course different from the others. We really wanted to make you aware of why things have been designed in that way. Sometimes you read C++ code, and if you happen to read the standard, sometimes doesn't really make sense. Why are these people spending their life in these things? There are usually very good reasons, and there are for implementation reason and for efficiency reason. C++ is designed to be efficient. This doesn't mean that your code will be efficient, but it may be efficient. That's the idea, all right? So there are so many different features, so many different ways of using them, that is very hard sometimes to remember what you do in one case, what you do in another case. Sometimes it's difficult to find out why you have some errors, like when I compile in debug mode, my code works. When I compile in release mode, it doesn't work, or vice versa. I say, what's happening here? And to do so, you need a mental model, at least. Right? You need to understand what are the mechanisms, why things are implemented that way. And it's difficult to get these mental models. Some are like abstract mechanism on how things could be implemented on a certain architecture. For instance, the C++ standard never mentioned the stack. I'm not talking about the STL data structure stack, but never mentioned the stack. Anyone knows what the stack is? I assume everybody knows. If you don't, ask. There's no problem. I can explain you very, very quickly. But basically, the standard never mentioned the stack, but is underlying everything many of the things that the standard writes is because of the stack implementation of the function called functionality, right? When you call a function, you put the argument on the stack, the address of the return instruction, then you put the local variables on top, and you go on. The standard never mentioned this, ever, because it wants to be open to every possible architecture, like microcontrollers. We had Ken, it was saying, working on very small hardware, very small microchips, and sometimes they don't have this kind of features. So the standard wants to be open, never mention the stack, but if you understand the stack, everything will become better. It will be nice to understand some of the optimization techniques. We will go into this, like inlining. String matching, a substitution, is a very good thing to understand templates. And Codalization, just if you want to understand name mangling in C++. I want to go into that right now. But basically, the mental model is like the mechanism, or abstract or not. It might be actually a concrete mechanism, but ideally is an abstract mechanism that explains how things work. So it will be easier for you to remember what happens when you do something. When you call a function with an object, and you call the move constructor, why does this happen? Well, this is a very nice mental model that explains why, so you are not surprised by the fact that it's not copying, but it's moving, etc. Any question? Ease. Too boring? Oh, yeah. Oh, the stack, yeah. The stack frame mechanism has been invented in the, I think, early 50s. And it's the mechanism that all compiled programming languages use to implement function calls and recursion. If I have I call a function f with a and b, and this is in my code, what happens is that the compiler keeps a special register in your architecture, your microchip has a special register, which is a stack pointer, that is pointing somewhere. So there's like all the memory locations down there. Now we say, okay, I'm going to call function f. Function f has a certain address in memory. I'm going to, for instance, this is just one way. Okay, it can happen in many different ways. I can take A and put it on top of the stack. The stack is a data structure which is a FIFO, first in, first out. Only two things you can do on a stack is push and pop. Push, you put something on the top of the stack. Pop, you remove it. Okay, the only two things you can do. So you say you push A on the stack, and you push the value of B on the stack. Then you say, here I'm calling this function in address, I don't know, 100. This is the address in memory of that instruction. I can write 100 here. And then I jump into address of this function. Let's say this is a 500. I go to address 500. This function is doing something inside. What does it do? Well, it allocates some temporaries. For instance, the typical integer I variable. And we'll put it on top of the stack. Then we allocate J, and we put on top of the stack. And we'll start using these things. It might be calling other function. It calls a function G. You put the argument X in here. No, sorry, X is not be. You put argument I in this stack point. It puts the return value, whatever 510, the instruction when the function call has happened, and here it goes. When the function exit, it just goes to it jumps to this address, and the flow continues. So when I'm here, and my function f, this is called the stack frame of my function. When the function exit, there is also a placeholder for the return value, which is maybe here somewhere. Okay, but suppose it doesn't. Suppose it is a void function. It doesn't have a return value. Then the function keeps going on from here. So with this stack frame, so this stack frame is allocated on the stack very quickly. It doesn't need to do new statement or anything. It just put it there, increment the pointers, few pointers increment, and then you're done. Recursive function now becomes extremely simple because it will call f with some other arguments on the top of the stack, and you go on, and then you do the stack unwinding, and you go back. You go back where you are. This explains now, suppose that this code calls also a function h with some other arguments here. Now it get out of this function, so the stack pointer is here again, and now I call h, it will allocate the same stack value, the same pointers, okay? So for instance, if h use a variable which is not initialized, it will go and see what the previous values on the stack were. This is a typical error that might happen. If you don't initialize a value, you get the random value. It's not random at all. It's probably some other functions left over on the stack there. And if you're lucky, this is 0, everything is fine. If you're unlucky, it may be the pointers, and you get really confused sometimes. Okay, so this is the main thing that is going on since the 50s in all the compiled languages, like C, C++, Fortran. Fortran is slightly different convention for the subroutines, but this is how C++ does it. And it's using the same thing, basically the same old trick. It's not doing anything special. What it's doing special is that the function names are kind of weird and complicated, but it's basically the same trick all over the place. So if you have errors like, if I put a print, everything works. If I remove the print, the code crashes. This happens very, very often. It is because there is an initialized variable somewhere, and you go and read these strange values on the stack of someone else. Is it clear? Okay.